Okay, and Tuan, did I do your recording? Okay, it's there. Anybody else? Okay. So I finished all the last ones. I emailed them back, and then I made a curve the next day, and I'm going to give it to you right now. So let's try through the chat messages. I'm going to send it that way. Send a file. Okay. And then, how does this work? Open that one. I think this is it. Okay, so everybody look in your chat messages and you should see a file and you can take it and keep it. Okay. Okay. Okay, I'll let you stare at it for a few minutes. Then we have one subject for today. What I want to do is go back to the beginning of the semester and we're going to do GDB work. You sort of know what GDB does, but now we're going to practice it and make it your knowledge even stronger about it. Okay, so I have we better do this part. Okay, so we're going to do it live with a program, but first let's go over a few concepts, maybe for 10 minutes on the whiteboard. And so I got to find to share this, change the camera. How's this? Okay. And you know, everyone, I know already as a fact, the great big majority of all of you listening, you're not going to program an assembly when you get your big job. Maybe out of the 25 of you, one person will end up in an assembly role, but the rest of you will be programming in high-level languages, most likely. However, there is one thing from this course that you can take away with you and use it again without assembly. And what is that? That's the GDB tool. GDB can be used with lots of other programming languages. So we're going to spend today GDB delving more deeply into this, and maybe a carryover for half of next class meeting, but at least the whole day today is about GDB. Okay, so I keep looking to see if there's any questions you want to. I have the chat box open next to me here, and I'm glancing at it every once in a while. So what GDB, for 10 minutes here, let's go over some of the fundamentals. GDB is going to let us investigate not only what's in registers, not only what's in memory, but it lets us investigate how the mechanism works that calls one function calls another function. And there's two that are somewhat different. There's C++ that calls another C++ function. And there is C++ that calls an assembly function. And I think we had a couple of practice programs in the past. There was the case of assembly calling is float. That's calling a C++ function. So assembly can call C++ as well. Okay, and GDB lets us see it in real live action, how this call happens and how this call happens and how that call happens. So we'll get there pretty soon. Maybe, I'm not sure if we'll get there today, but we'll get awfully close to it. Okay, so here, before we go on, take note of these names of data sizes. Names of size of data. Okay, so I'm going to make a little table here. Across the top, it says C and C++. In the middle, it says assembly. Over here, it says GDB. And then down this side, it says 1 byte. Is this under the camera? I hope so. 2 bytes, 4 bytes, and 8 bytes. And draw across here, 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 here. Okay. You might ask, what happened to 16? The truth is it exists on only very rare, expensive computers that the public generally doesn't buy. Supercomputers may use a 16-byte register, but it's not available for the general public. The price tag is way too expensive. All right, but for the rest of them, these are the O words. We're not going to deal with it. So, what are the names here? In C++, that would be called a char. In assembly, that would be called byte. And GDB would also call it a byte. And these get abbreviations here. This is just B and B. All right. 2 bytes in C++ is called a short. And in assembly, that's called a word with a W next to it. And in GDB, it's called a half. With an H next to it. Okay, you still here? For 4 bytes, that's called an int, or it could be called a float. In assembly, that's called a D word, meaning double. And it gets known with a little d. That's its abbreviation. And in GDB, that's called a word. So in GDB commands, we use a W. And then in C++, 8 bytes is known as a long or a double. And in assembly, that's known as a quad word. And we use a Q for that. And in GDB, that's known as a giant. And of course, we use a G for that one. Okay. Assembly has we call this an O word. That's not zero word, that's O word. I don't know what the letter is. It's probably just O. And I have never seen it in GDB, and I haven't seen it in C++. But if you wanted the future of 16-byte registers, they're full of O words. Okay, questions. Did you get the link to the curve? Did you people pick up the file? It's very short, 169 bytes. Jesus didn't get it. Greg, it's in the TXT. Okay, Greg, help him out to find that file. Okay, so something else. Okay, here just to refresh your memory, it was way back before the spring break. For looking at data, I'll call it under the category of viewing data. There's two ways. One begins with the letter X and a slash, and it needs 3 parameters here. And then you need a data object. Plus, I'll just write the word object. Okay. And the other one, of course, is P with a slash, and you need 1 parameter and an object. Okay. So the X command has built into it a kind of dereferencing. It's automatic. Dereference. And I'll write an example. Okay. P doesn't do that. So let's take the register RAX. If you want to see what's in RAX, it's P/X $sign RAX. But if you use the X command, you don't see what's in RAX. It takes what's in RAX and treats it as an address and goes to that address and then shows you what's in memory at that location. So it would look like PX/. Now the three parameters are, one is a number, a plain integer number, like I'm going to use 1. The middle one is the formatting, like hex or decimal or binary. So I'm going to use X. And then the last one is the group size of each number. And that goes back to this thing, one of these 4. So I'm going to use giant for 64 bits, $sign RAX. Okay. So the first one shows you what's in RAX. The second one, because of the automatic dereference, uses what's in RAX as an address, goes to that address and shows you what's at the address. Everybody's got that? Okay. So here's we could say X/1, D for decimal, G for giant, $sign RCX. We could say X2 decimal. So let's use my finger here, word, $sign R10. Okay. So this means go to R10, which is 64 bits, pick that value up as an address, go to that address, and starting at that address, show me 2 numbers. Both of them are of word size, 4 bytes, and both of them are in base 10 decimal. So you'll get 4 bytes displayed as a decimal integer, and then the next 4 bytes immediately after that will be also displayed as a decimal integer. Okay, so the third parameter is from this table over here. What size do you want each individual number to be displayed as byte 2 bytes, 4 bytes, or 8 bytes. And the D, I don't like to say it, it's the base of your number, but it kind of is. Here's one more example. X/4 floats W $R15. So that means use what's in R15 as an address. Go to that address and use 4 bytes to form an IEEE floating point 32-bit number and display it. And do 4 in succession, address successively from that point forward. That indicates 32 bits. That indicates float forming, 3.75999. And the 4 says you're going to get 4 of these numbers in numeric sequence by addressing. Okay, any questions? Okay, next, I was going to point out, prefixes. Prefix. $, or ampersand, or star. So $, has to be placed in front of all registers. All registers. XMM included. Like back here, I've got a $sign in front of every one of those. Okay. Just like in ordinary C++ programming, ampersand means address of what follows. Okay, and the asterisk means take what follows from after the asterisk, treat it as an address, go to that address and find the value. So follow to the real value. Okay, let me see if we got any more notes to go. We're going to go live in a moment. Okay, so watch this terminology, everyone. Terms. There is statement, instruction, and a command. Okay, so this one belongs to C++. This one belongs to assembly. And this one belongs to GDB. GDB. Actually, it also belongs to Bash as well. Okay, so one individual executing thing in C++, we call those statements. Your programs are full of statements. In assembly, one executing thing is called an instruction, and in GDB or Bash, one item to be executed is called a command. It's all about the same thing. Okay, one more is code numbers, code letters. GDB codes. Is this in the camera range? I hope so. Okay. So here I'm going to give you the whole list of 9 of them, although only about 4 are commonly used. So letter D, and where do these go? These are the middle digit, that middle parameter. There's an X, there's a D, there's a D, and there's an F. See, the middle one means something. So what are the codes for the middle parameter? D means signed integer. And C means char. And A means address. And S means string. And I means instruction. That's an assembly word. Okay. And U means unsigned integer. Two more to go. T means binary. And X means our old friend here, means X. Okay. Those are the items you can use in the X/ command. X/ and then you need 3 parameters here. These are the codes for the middle parameter. Okay. All right. Do I have any more to tell you about? I don't think so. Okay. I'm going to try and find the program now. So a lot of what you're going to see is, I know we reviewed, I first did this with you a month ago, and then we had the midterm and the spring break. But like I said, this may be the only thing you ever take away from this whole assembly class, because this is usable in other programming languages. Okay, let's see what we can do. Actually, we won't need this. I'm going to share the screen with you. So let's give me half a minute to find the program we want to run. Let's see, where is it? Okay. System. I know I'm taking time. I'm trying to find the where I left it. It might be here, and it might be here, here. Let me check this one. No, didn't work. Let me try another. Can I find something good here? Okay, I think I got it. I think I got it. Okay. And I think I might even have used this same program in the past, but it's just a good practice area. Open it with, where's the source? Okay. Okay, hang on. It's coming, it's coming. Okay, let's share screen, and you'll just see the whole thing. That's the whole share desktop over here, right there. Okay. So here's a program. It was created artificially just to test GDB. It has no real purpose. We want to practice getting access to arrays. They're harder than ordinary variables, and we want to be able to change the values inside of arrays and use the right code letter depending on their data types. So we'll try it. And then towards the end, here's one dynamic array, and we'll find out how the addressing goes for that kind of special array. Okay, so let's run it. ls-l and shrg.sh. Let's go stretch the screen a little bit. Okay, there's no errors. If there were errors, like compiling type errors, it had shown up in this area where it's green, but there's none. You should always put at least one break. If you don't, the program runs all the way to completion and you never get to investigate any registers or anything. So if nothing else, I always make a break with main, M-A-I-N. And I think that's all we need. So let's run this program. So it's the same program that's in the back here. See, it's going to say welcome to GDB, and then it's going to say the purpose of this is. So right here it says the next statement I'm going to execute after the word main is welcome to GDB. So the letter N means next execution. Now it's going to execute this thing. Next. And it out. It did it. Here it says the words known universally as GDB. It produced what this output statement said it was going to do. Okay, now it says it's going to create this array A, and those cells, the individual numbers, are quad words because of the word double, and there's 6 of them. It's declared for 6, but you notice there's only 5 numbers: 2, 3, 4, and 5. And one more thing is GDB tries to save space on output by truncating zeros whenever it can. Zeros on the left, zeros on the right. And watch, whenever it outputs 12.0, it's just going to output 12. And if you didn't know any better, you'd think that's an integer 12, but it's not. It's IEEE 12. Okay, so let's investigate. You remember some of these from the past. How do we find out where A is? Like that. Okay. And I should, where's my chat messages open? Okay. It tells us the address where A is stored. That's pretty nice. But how does that relate in relationship to the front and back end? Okay, so let's look at the back end. This should be a large number. PX $ is required RBP. Okay, and look at it closely. You can see that that value, that address is larger than the one where A is. And how about the front end? SP. And if you look closely, that one's smaller than where A is. So that says that A is between the front and the back end of the activation record. A must be inside the activation record. Okay, got it? So from before the midterm, we had a formula to tell us how many quad words are in the activation record. And do you remember that? It looks like this. $R, the big number minus the small number, divided by 8. That's the number of bytes in a quad word. And then it's always off by 1, so you add 1. Okay. What does it tell? It tells us there's 37 quad words in the activation record. Now, let's use the dereferencing principle to see them all. So x/ we're going to send it to where RBP is, not what's in RBP, but the using that address in RBP, go to that location and then show us everything. How many we want? We want 37. There's the first parameter. Let's show them in hex. And these are all quad words, but the new code number is G. New code letter is G, $RSP. All right. So you know the terminology. This is the front end of that activation record. This is second to the front end. This is third from the front end. And here's the back end. Front end, back end. All the others are caught in between. And there's something special here about the back end. Remember that the back end is going to, in most cases, will hold the value of RBP from the previous activation record. But look, this is main. Main doesn't have a previous function. There is no previous activation record. So this is what created by C++. C++ compiler has to put something there. And a lot of the times it will be just all zeros. But there's enough times when you get all zeros and a 1. Those are markers that this is the activation record with no predecessor. There's nothing that came before it. Later, I don't know, we might get to it tomorrow, next class meeting. We'll see whether there is RBP written into that place. All right, and here's the front. Now, what happened? This is front. What happened to our array? Our array is located here. And you go to DEB0. DE, where are you? Here. DEB0. And well, we're supposed to find 2.5 at DEB0, but there's no 2.5. That's full of garbage. And here's the second number in the array, all garbage. Third number, fourth number, all garbage. Fifth number, all garbage. And the sixth number has a 6 in it. I don't know why. But we know the sixth number was never declared. It was left out of the initialization. So why is that? It's because when this command was executed, statement number 21, line number 21 had not executed yet. The A had not been created, but the compiler knew the space for it. DB, I lost the place, DEB0. The compiler knew I need 6 quad words, and it set up those 6 right there, even though they're filled with garbage. That's reserved for A. So what we should do is execute the next statement. Next, they're executed. And what it shows is the one that will execute next after the one that just happened. So B hasn't been created, but A has been created. And if we look at the activation record, we should be able to see A. DEB0. Now it's changed. That looks like a real IEEE number. How can you know? Well, you have to kind of memorize that when the exponent is 400, the number is 2.0. But this one is 400 plus a little bit extra. And so it's 2.0 plus a little bit extra. And how does that work? Well, it comes out to be that one. That's not bad. What about the second number in this array? DEB0. So we looked at that one. And then here's the second number. It's 400 with a lot more extra. So it's 2.0 plus a lot more extra beyond. And what did I say? This is 4. This has to, oh, you know what, the class, I'm looking at the wrong array. That's B. I have to go back to here. Okay, there's 2 point. The next one is 3.5. Okay, and it's about right. DEB0. Okay, when this number 400 reaches 401, then we're at 4. but we're not quite yet at 4. And then that matches what we expect here. It's actually 3.5. Okay, what's the next one going to be? 4.6. DEB0, it would be over here, 4.6. And you notice it's 401, that is 4.0. And then this is a little more than, because of this mantissa, it's a little more than 4.0. Yeah, it's actually at 4.6, it says. Okay, I won't keep going, but is our 12 there? 12.0 and the DEB0 first, second, third, fourth, fifth. This should be 12.0. And 4.2 is 8 plus the number 8 starts with a 1. That's halfway between. The next value up is 16. So it goes from 8 to 16. This is halfway in between. Yeah, it's a 12. That matches. And the last place, this was a 12. This one's still 0. It's waiting for a number. All right, there's analysis of. Now, here's a hard one. What's the command to show us that entire array A without all this other stuff? Let's try P slash, I don't remember. P slash decimal, no. P float A. I don't know. I don't think it's gonna work. It did work. Okay. Okay, put that in the record book. To look at all of the components of an array, use P, no ampersand in front of the A, and it got it pretty good. Now, it's the lesson learned in this thing is this one can't show us 4.6. It wants to, but it can't get there. This 4.6 up here is not a binary expressible number. This is the closest bit combination it can make to get to 4.6. Here is the next number. A fraction of 3/4 is easily expressed as 1/2 to the first plus 1/2 to the second. You add them together and you have an exact number. That works. Here's 12.0, but it shows it to us as a integer. And I'm sure that's just for space saving. It doesn't want to go to the trouble of showing 12.0. It's not an integer. It really is in IEEE format inside. And there's a 0 on the end. Okay. I should look. Any questions? No questions. Okay, this should sound sort of like review, but I hope it's solidifying in your mind. Let's go for the next one. And there's a long bunch of 5s. Let's execute that one. Now, did that last command still work again? If we want to view what's in our array, if I said float, that wouldn't come out right. So I should say integer and C. That works pretty good. Okay, here comes the next one. Now, this is tricky. Here's D. It has 2 negatives and a positive, but they're 32-bit numbers. So outputting, I don't know, will this handle it correctly? Let's try. Did we execute that one? Oh, we better execute it first. Okay, now we can see what's in D. P slash decimal, and D is its name. That's not hard. How about, what if we wanted in hex? Would that work? P slash X D. Ah, isn't that interesting? It knows, GDB knows this is a 32-bit number. See how it gave us only 8 digits instead of the usual 16 for -1. And here's -2. Works nice. And here it worked. That's working okay. Is this in the activation record? Okay, let's see if you can. Let's I'm going backwards to where it was here. Okay. It's hard to find. Let's see. Whoops, what happened here? Okay. Does anybody? Oh, we better find out where it's located. P/X address of what's the name of it? D. It's at DE54. DE somewhere in here. That looks like a -1, but I can't figure out the rest of it. So you know what the problem is? This is unreadable because those are quad words, but the numbers in D are just what's the right word for it? They're 32-bit numbers. So why don't we fix the display of, let's fix this so that we display it not as giant, but one size less, W. And I'm going to increase the number of words. 64. Okay. And where is it located? It's located at DE54. Close to here. This is DE50, DE51. Oh, no, you have to count by fours. DE50, DE54. That's our number. It said it was at DE54. That's -1. DE58 is over here. That's -2. And DEC, add 4 to the last one. There's the number 3. That's that array. Just stored right in the activation record. But it's easier to view it if you use the right size, because that's a size 32 bits. We want to show it in terms of 32 bits. Okay, any questions? Okay, you can all handle this easy stuff on a concept test, can't you? Okay, this is a hard one. Coming up is an array that says hello. Okay, where is this stored? P/X ampersand F. It's at DF22. Okay. Wow. How can we see this whole array? P/, oh no, what should we show it as? Not string, character. Yeah, and its name is F. That doesn't look pretty. That looks kind of ugly. How about P/string F? No, that gives us the ASCII number of each character. P/S. There it is. That's the one you want to make sense out of hello. Okay. You got all this copied down, or else you're recording it, I hope. Let's see. What's next? Oh, there's that true false statement. Here's a Boolean. These are 1 byte each. Okay. So let's execute it and see where they show up. We just executed it. And now let's use the P/ about integers of that Boolean one, G. That's pretty good. It tells you that true is 1 and false is 0. It just matches completely. 5 bytes, and each byte holds a 0 or a 1. There's a Boolean array for you. Um, so where is this stored? P/X AG. It's stored at 4F. What a mess that is. That's way off the boundary. That isn't anywhere nice. Okay, so if I did, which one shall we do? I'll go backwards and find the last one. We should do this one. Oops, didn't mean to do that. It's at address DE4F. DE4. Oh man. DE4. I don't know where that is. Okay, here's how we figured it out. To make life simple, it's showing it in 32-bit groups. How about we show it in 1 byte groups? So this would be is it? Let's do it in decimal, and 1 byte is byte, and we'll see if we can find it. Okay, so it's supposed to be located at DE4F. Okay, so this is 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, not 49, 50, 49, 49A, 4B, 4C, 4D, 4E, 4F. That's our guy. 4F is where that array of Boolean starts. Okay, so the first one is 1 for true, then it's false, false, true, true, and then it goes off into somebody else's array. We located it. That's it. It's right there. It follows where its address predicted it would be. True, false, false, and true, true. That was the array. Okay, so what else do we have to do? Going back here, we did this array here, and then there's some uninitialized thing. We'll skip that one, but we want to study the dynamic one. Got it? Okay. So just in case dynamic shows up on the test. All right. So let's go next. That's starting it. The next statement is going to create space for this dynamic array. Actually, the spaces are, oh, is the space already there? No, before we go, P/X ampersand, ampersand I, DE30. Okay, let's, we gotta watch this change its value. Is that right, X? I just want to fix this. I want to see quad words. G, okay. Oh, the number is too big. 64, it was supposed to be 37. So, okay, now this is a dynamic array. We go back here and get it. It's located at DE30. I think there's nothing there now, right now. DE30. That's right here. See, there's nothing there. And its successor, there's still nothing in this array. And then there's some junk. All right, well, and the reason is it hasn't been created yet. When we left off, it was it was ready to create it. And so we found the space for it, DE30, and found that it's all blanked out. It's all zeros. So let's create it next. Next, create it. Okay, and then look at that same DE30. It changed. You notice that? It was DE30, all this stuff. But now it has this number in it. And then I'll let you guess. That plays a special role for hackers digging into how your computer works. Um, that array claims it's located at DE30, and when you go there, you find this number that has nothing to do with the first, what's stored in slot 0. So let's execute. Create it. We'll put something in slot number 1, put something in slot number 2, and then go back and look at that DE30. Nothing's changed. Notice that? Now, if this were an ordinary static array, you'd find the 3 numbers there, 100, 32, and 5. But this dynamic array, and so you don't get anything yet. So what's the trick? The trick is that number is very small compared to these other addresses. Notice these addresses out here. That's 12 or 14 hex digits. It's a big number into the gigabillions. But this is very small, 418,000. Now that's a small number. So what we want to do is trace it down. Let's do x slash 3 numbers in this array. And we're going to look at them in decimal. And these are, what size is this array? These are quad word size. Yeah, it's type long. They're quad words. Okay. So we'll go giant, and then I'm going to take this guy, this whole thing, copy it, put it down here. Oh, I don't know why it blacked out, but it doesn't matter. Okay, I press enter, and guess what? There's the array. It was stored as 132 and 5. And you can see back here in the source code, it got 132 and a -5 actually. Okay, so that's not in the activation record. Those 3 guys are in heap space. In fact, they're very deep into heap space. They're at such a low address. We'll find where you can't get to the address, just slightly smaller than that one. Okay, so a dynamic array, the way it's managed by C++ is put a number, an address number, where we think the array should be. Okay, this is where you think the array should be. Ampersand, what's its name? Yes. It should be here. But when we go there, what it gives you is this one. And that's an address where the actual data, the true data are really stored. And then we go to that address, and then over here it tells us you're at this address, and this is what I find here. Okay, you got that? That's how, not all languages handle it that way, but at least C and C++ handle it that way. The dynamic arrays are placed in this low memory address space, commonly called as heap space. Okay. Now, that's saying dynamic arrays are ones that put their data values in the heap is not the correct definition. That only applies to some languages. The correct definition of dynamic is this is an array where the compiler does not know how many elements are going to be in the array. Or better said, the compiler does not know the size of this array at compiling time. If it did know the size, the C++ will put it in activation record. Okay, so watch this. Let's do what a, that number's way got too many zeros. We're gonna take some out. Okay, GDB doesn't care. So there's the number, and it leads to our array. Now, what if the number is really made much smaller? Instead of 400,000, it's like this. That's 400,002. Okay, it finds three integers there, real ugly integers. What if it was 400,000 even? It finds three other integers. You don't have to restrict yourself to three. You can ask for 8 integers in succession. Oops. Did I hit the right key? I think I garbled something. Sorry. What did I'll put an 8 there and try and fix myself. 8 GB. Okay, there you got 8 numbers that are close to 400,000. In your mind, can you subtract 1 from 400,000? We're going to go 1 less than that. So you subtract from 400,000, that would be 3FFFF with 5 Fs. 3, 1, 2, 3, 4, 5. Okay. And what does it say? It says you're in an area of memory where you cannot see what's there. We're not allowing you to see what is stored there. And I tried a lot of these. 400,000 is the break place. 400,000 above, you can access that memory. You go one number below, and you can't. Guess who's blocking access to that address I just used? Hey, like this guy. If I go one lower, it would be an E. He says you can't have this. If I go a whole lot lower, it says you can't have this one. So this is getting really low addressing compared to everything else. That's where the kernel is living right this moment. The kernel lives in memory space from address 0 up to, but not including, 400,000. Okay. I wonder if there's any more we want to do with this thing. Oh, the rest of this program is not very interesting. Okay, this program has no float numbers in it. I guess these arrays have float numbers, but there's nothing that it does that uses XMM registers. So let's see what we can do. How's our time going? I got about 10 minutes to tell you about. Then we're going to quit. Okay, you need to know how to access XMM registers. They all have to have a $sign in front of them, and we can. Let's do PX $sign XMM0. Okay, now the problem is XMM0 in its complete totality has 128 bits. If you split it in half, then you have 64 and 64. And those are called components. But if you split it in 4 pieces, then you have 32 and 32 and 32 and 32. Okay. So it's just a matter of how do you want to split this up. And here's how they do it. You put a dot, let's split it in half. That would be a V2, and I think it's an underscore integer 64. Okay. So we're going to treat those two numbers like integer 64. And I forgot one more thing. There's 2 of them. So we have to tell it which 2 do you want. The one on the far right side is called number 0. But if you wanted the number on the left side, it would be number 1. Okay, so let's go for 0. And now why did, I'm a little confused. It looks so small, but it's probably because GDB is truncating leading zeros. Let's do the adjoining number, 1. That's all full of zeros. I need to find a register that has something in there. How about 2? Okay, there's a horrible mess. That's it. It didn't truncate anything. There's 16 hexadecimal digits, and it's showing us the whole mess in hex. Okay, there's only 1 and 2. Let's break it into 4 pieces. Okay, so that would be type integer 32 bits, and then we can look at the one on the far right, which is considered to be number 0. Oh no, I did something wrong. Uh-oh. It doesn't like the int 32. Oh, no, I know it. Yeah, dumb. You have to say 4 because there's four pieces. We cut it in 4 pieces. There's our number. And then you can go and get number 1. There's our number, and there's number 2. There's the number, and then there's number 3. And there's its number, and there's no number 4. It doesn't exist. Okay, so I see. I now remember. If you're splitting it in 4 ways into 32-bit floats, then you have to say V4. If you're splitting it in halves, you say V2. Now let's go one more. What about not in hex form? What if we want actual numbers? So let's do a. I want to go back to 2 and underscore int 64 and no, slot 0. But can we see this as decimal integer? Same data, just want to show it as decimal integer. Pretty big integer. Yeah, okay. Can we see the same data as a float number, type double? Yes. Well, we have to change something. This has to become a double. And this guy over here has to become float type. And it looks okay now. And this is it is float, but it's in scientific form. It says, this is a base 10 number. You can see the fractional part, but you have to multiply by 10 to the 174 to get its actual value. Kind of ugly, but let's see if there's one that's more pleasant. Put a 1 here. And not much better. What if we did register 6? It'd just be nicer. Oh, it's a NAND. Remember, it's a negative NAND. It's the first bit is a -1. So okay, so here's the common one last pass. Here's the common usage when you're accessing floating point registers. One P/F, and then name your register, $, XMM15 dot. Now, are we going to look at half of it or fourths of it? And you have to pick V2 or V4. I'll pick V4 just to be different. Underscore, and now I'm choosing a floating point form. If this was 64 bits, I'd say the word double here, but I'm going to say float. FLO, float, FLOAT. And then pick a number between 0 and 3. Let's just go 0. Oh, it holds only 0. Now, I would have liked the GDB to put that out as 0.0 to tell me it's really a floating point 0, but they didn't. We're getting all zeros. Let's pick something else. 0. The whole thing is full of zeros. Okay. So I can't find one. So I wanted to make a summary. P/F. You pick a floating point register, XMM anything, dot, and decide if you're splitting it into 4 pieces of 32 bits each or 2 pieces of 64 bits each, and use either V2 or V4. V2, then I have to say underscore double and pick a number, 0, 0. Okay, there's that guy. If you want to see the same data as in hex, it's P/X $ XMM2 dot V2 underscore int 64 bracket 0. Okay, that's the same set of bits as the previous one, but now expressed as an integer in hex. And if you wanted it expressed as an integer in base 10 decimal, it looks like that. Okay. What is it? I'll try one more. We're almost done, class. So what if you took the 264 registers and you smack them together and you have a 128-bit register? Can we do that? I think you can. P/B $ XMM2. I like 0 for some reason. Dot INT 128. That's how many bits there are. Hope that works. That was the wrong thing. Oh, I think it's I think it's a U. That's not very big, is it? There's a lot of leading zeros that have been truncated away. Okay. Okay, so what if we just said that's a nice integer, but I'd like to see it in base 2. Okay. There's a lot of leading zeros that have been truncated away. I'll try one more with 2. There's a 128-bit binary number. Could we see that as, oh, how about in hex? Yeah, that's more than 16 digits. That's a big number. So it does allow you to use all 128 bits. I just don't have much experience with it, but they're all there if you ever wanted to use it in your assembly programming. That's an astronomical size number. Class, how's our time going? I'm going to pause here. One more thing I'll do next class is we want to look at how a function is called when it's passing those data values and how it creates a brand new activation record and it links the new one into the or there's a reverse order. The old one gets linked into the new one. I mean, I can lecture about it and I can draw pictures on paper for you, but there's nothing real like actually seeing it happen, and it makes it come home. It makes more sense out of it. Class, I'm now concluding. I'm kind of I have many things to be. My story is that I have so many things going on at the same time. I am working on your programs, your midterm programs. I really am. I'm trying my best to get through those, but in a day's time, there's so many interruptions with other activities. It's hard to get a big block of time where I can grade a lot of them. I haven't forgotten you. You will get them back with a numeric score from 0 to 100 on them. So you just got to hang in there, and I'm doing my best to catch up with those midterm programs. Any questions, anybody? I'm going to conclude here. If you haven't worked on the last posted assembly program, that's good practice material for the final. You know, I make a comparison with the music majors. They play songs every day for a month, and then they get a recital and they get a grade. That's sort of like what we're doing. You're supposed to be practicing programming, and then eventually comes the big day, the recital day, and then you'll get a score on it. I wish I had TAs and assistants that would help grade things, but actually there are actually those kind of helpers are hard to hire, I've been told. Dr. Bain says that she looks and looks for people to take these kind of jobs and nobody wants them. That's why I'm way behind. All right, everybody, have a nice afternoon, and I'll talk to you all on Thursday. Keep in mind there's an SI meeting tonight, 5:15. If you go, tell the group leader that tell the SI leader you've been learning GDB in class, and see what his reaction is. He knows GDB pretty well. Okay, have a nice afternoon, everyone, and I'll stop sharing here. And I'm still here. Camera back here. Okay. So I'll see you Thursday, everyone.